Hi, my name is Ellie Hecker, and this is my Lab 4 on circuits and capacitors. The purpose of this lab was to gain an understanding of the behavior of conventional currents and potential differences by using ammeters and voltmeters to experiment with different components of a circuit. For the first part of the experiment, I found the currents I1 and I2 to be 0.02, which held true in both my calculations and the computer simulation. In the second part of the experiment, I found that the time dependence for charging and discharging the capacitor was 6.84 seconds. Some of the most important physics principles used in the lab were energy conservation in the loop rule, charge conservation in the node rule, and Ohm's law, which states that delta V equals IR, which means that the potential difference is equal to the current multiplied by the resistance. We first predicted the current for the circuit shown here using Ohm's law, which states that V equals IR. We have two batteries at 1.5 volts each, giving us a total of 3 volts. R is equal to 147 ohms because we had 47 and 100 for each of the two resistors. Using these, we can solve for I, giving us a predicted value of 0.02 amps. We then set up that same circuit in the computer simulator in order to determine the currents I1 and I2. The ammeter read 0.02 amps, which matches what we just previously calculated. I also found that if the connection of the ammeter is reversed, then the current is equal to negative 0.02 amps. Next, I replaced one of the ammeters with a voltmeter and found that the potential difference in the circuit is 3 volts, which we can conclude as a result of the total voltage from the two 1.5 volt batteries. The second ammeter now reads 0 amps because the circuit is now open where the voltmeter was placed and the current cannot flow through an unclosed circuit. Next, we wanted to find the voltage difference at several places along the circuit. A reading was taken at each of the locations shown in this top right diagram, and the results of the readings are shown in the table here. If you sum up all of these voltages, you end up with 0 volts round trip, which tells us that the potential difference is 0. It is important to note that when we were taking those readings, the voltmeter did not affect the current because the voltmeter has infinite resistance, meaning it has no effect on the overall current. Although we next added an ammeter in parallel with the 100 ohm resistor, which caused the ammeter reading to change to 0.06 amps, as you can see in this bottom right diagram. This change can be explained by the node rule because the current is now split up between the ammeter and the resistor. Next, I calculated the actual resistances of both the resistors, the wire, and the ammeter. To do this, I used Ohm's law, which states that R equals V over I, and I plugged in the voltmeter readings for V and the ammeter readings for I. My calculations are shown here, and I found that the 47 ohm resistor had a true resistance of 47.95, the 100 ohm resistor had a resistance of 102.05 ohms, and both the wire and the ammeter had a resistance of 0 ohms. In the next part of the experiment, we looked at the capacitor and time-dependent voltage. By connecting a battery to a light bulb and a capacitor in series as shown here, we were able to observe the charging of the capacitor and found that the light bulb started bright, and then as time increased, the capacitor charged, the bulb dimmed, and the current slowed down. When the capacitor is fully charged, the bulb turns off and the current stops flowing. By disconnecting the battery and directly connecting the battery and the bulb as shown here, I was able to observe the discharging of the capacitor as time increased. The bulb dimmed and the current slowed down until the capacitor was fully discharged and the bulb turned off and the current stopped flowing. We can also see that the current was reversed when the capacitor was discharged. Using the stopwatch, measurements were taken of the number of seconds it took for the capacitor to fully charge and discharge, and this was done using both the 10 and 20 ohm bulbs. The results of my measurements can be seen in the table. With the 10 ohm bulb, it took the capacitor 10.24 seconds to charge and 12.91 seconds to discharge, while with the 20 ohm bulb, it took 19.98 seconds to charge and 23.78 seconds to discharge. These measurements make sense because as the charge of the bulb is doubled, we can expect the time taken for the capacitor to charge to nearly double. Next, I recorded the instantaneous voltage every 20 seconds and used these to calculate the RC value. The third column shows ln of V over V naught, which was used to linearize the data so it could be plotted in this ln of V over V naught versus time graph shown here, which provides us with a line of best fit of y equals negative 0.1461x plus 0.0747. Using this data and the line of best fit, I can find the value of RC through the following calculations. By rearranging the equation, delta V equals delta V naught times e to the negative t over RC, we find that the slope of our line must be equal to negative 1 over RC. According to the line of best fit, our slope is equal to negative 0.1461. In solving this, we get a final value of RC at 6.84 seconds, which agrees with the computer simulation, which shows us an RC value equal to 6 seconds. In conclusion, if this lab were done in real life and an actual ammeter was used, then there would be a decrease in the current across the circuit. A real-life ammeter would have a small resistance, and since resistance and current are inverses of each other, as the resistance increased, the current would decrease. If we used a real battery to charge a real capacitor, then it would take slightly longer than it did in the computer model. In the model, the capacitor is charged instantly by the battery, but in real life, there would be a resistance throughout components of the circle, such as the wires. Thank you.